In this video, I will continue discussing linear regression, this time focusing on building up to the computation of the line of best fit. In part 1 of our linear regression tutorial, I explained that linear regression is simply taking our data and fitting a line to it in such a way that our predictions are as close to the actual value as possible. To get this line to fit our data as well as possible, we need to understand the components of a line. Let's start with the equation of a line. You may remember this from school. Our equation is simply y equals mx plus b, where y equals the y-coordinate, m is the slope of the line, x equals the x-coordinate, and b equals the y-intercept. Here we can see I plotted an orange circle on the line with the coordinates 2300, 580,000. We will use this point to understand the variables y, m, x, and b. This image illustrates the y-coordinate. This is our dependent variable, the value for which we are attempting to predict. We can't predict the values without m, x, and b. In this case, our y value is 580,000. This illustration shows the x-coordinate. The x-coordinate for this point is 2300. Here we can see the y-intercept, which equals 70,000. In simple terms, the y-intercept is the y-coordinate on our line when x equals 0. The final value is our slope, denoted as m. You may remember slope from the saying rise over run. Slope simply tells us how steep our line is. So essentially, we are trying to find how many units up or down our line goes for every unit it moves to the right. In this example, you can see for every 1,500 units we move to the right, we must move 330,000 units up to stay on the line. We can calculate this pretty simply by taking any two random points on the line. With these 2 points, we can use the formula y2 minus y1 divided by x2 minus x1. In this case, our slope is 330,000 over 1,500. Which simplifies to 220. In the context of this house price example, this means for every additional square foot of house size, our predicted house value goes up by $220. This is a diagram of the slope of 4 different lines. One with positive slope, one with negative slope, one with no slope, and one with an undefined slope. This line has an undefined slope because the denominator of our slope equation, that being the change in x, will always be 0, and we can't divide by 0. But you should know that as our line becomes closer to vertical, it becomes closer to positive infinity or negative infinity, depending on which way the line is pointing, as you see in the first 2 plots. So why talk about the equation of a line and specifically slope? Well, remember, our line is our model, so in order to understand how we can adjust our model, we need to understand the components of a line. You can see here 4 different graphs with 4 different models. The first 3 are poorly fit and thus not very good models. The 4th line fits our data very well and is a useful model. Notice the equations for each of these models. There are only 2 things that change: the intercept and the slope. Machine learning, in its most simple and basic form, is fiddling with these numbers so that we can make a prediction that is as close to the real answer as possible. An important thing to note is that in machine learning, we tend to ditch the word slope and refer to it as a weight. I think the word weight is actually much more intuitive, because what we are really doing is weighting each variable to give it a certain level of importance. The more positive or negative the weight is, the more it affects our prediction. The closer the weight is to 0, the more insignificant the variable becomes. Remember, this is because we are multiplying our weight times our input, so if our weight is 0, multiplying by our input will equal 0, thus making the variable irrelevant. In this slide, I show how predictions are made by simply plugging the numbers into the formula. For example, what is our predicted sale price at 1,500 square feet? Well, I know my slope, now which we refer to as a weight, is 220, and my y-intercept is 70,000. So I just need to plug in 1,500 as my x value. I multiply 1,500 by my weight of 220 and add the y-intercept of 70,000. We end up with a prediction of 400,000. So if my input, the square footage, is 0, presumably this means there is no house on the property. It is just empty land that we are buying. According to the model, the property is worth at minimum $70,000, but for every square foot we increase to the house size, we predict the sale price will increase by $220. This is the significance of the weight. It is telling us how important one increment in our variable contributes to the final prediction. So again, an increase in 1 square foot to our house size contributes to a $220 increase in our value, according to this model. While we may be familiar with the equation of a line being represented as y equals mx plus b, in machine learning we will often see it represented as y equals beta 0 plus beta 1 times x1. These 2 equations are the same, just denoted differently. Beta 0 being the y-intercept, beta 1 being the slope of x1 and x1 being our x variable. In machine learning, we typically have more than one predictive variable. So in our example, we are predicting house price based off square footage. But what if we wanted to predict house prices with square footage, number of bedrooms, and number of bathrooms? Now we have three variables. Our equation for a line of y equals beta 0 plus beta 1 times x1 is no longer sufficient. With three variables, we need an equation that looks like this. Y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3. Our x values, 1, 2, and 3, correspond to the variables square footage, number of bedrooms, and number of bathrooms. Thus, if we wanted to make a prediction for a house that had 1,500 square feet, 3 bedrooms, and 2 bathrooms, we would plug our numbers in as such. Beta 1, beta 2, and beta 3 are our weights for each variable. As explained earlier, we need to adjust these weights so that our model can make as good of predictions as possible. In the next video, I will explain how this happens using an algorithm called gradient descent.